All right. Good morning, everyone. I hope you had a great weekend. How's your weekend going? Anything you want to share with us? What did you do during the weekend? Yeah.
I had a sleepover.
Just relax and.
I went to office hours.
Okay. That sounds like a fun weekend. Anyone else want to share with us what they did over the weekend? Yeah, I was running and I ran into Michael during the weekend. All right. So today we're going to have a what I call the midterm review. But this is not a midterm exam review. This is a mid of the term review of what we've covered so far. And the goal is to really to help you see how everything that we have talked about fit together into this global picture of digital design. And a little bit boost up your motivation, for the rest half of the quarter. So we started our conversation in this class with number representation. We talked about tally mark, which is base 1. You put down like one stroke for each unit of magnitude. And then that gradually evolved into Roman numeral, which is an additive system. So V represents 5, X represents 10. And to get the magnitude of a number, you just add up those numerals. And finally, until we have Hindu-Arabic numeral, we have a positional number system. And in a positional number system, there's a fixed number of numerals. Typically, it's 10 from 0 to 9. And you just have to put them in different orders to represent arbitrarily large or small numbers. And if I were to compare these two representational schemes, I would compare them in terms of how compact they can represent numbers, what is the learning barrier for the whole society to accept these representations, and are they arithmetic friendly? So in terms of compactness, tally mark is very non-compact. If you want to represent a number like 1024, then you need to put down 1024 different tally marks. Roman numeral is a little bit better than tally mark, but it is still not quite compact. We saw that 1,888 on a building, and that takes about like 10 numerals compared to 4 in the regular positional number systems. So positional number, obviously, is very compact. In base 10, you grow exponentially as you're putting down more digits. 10 to the power of 0, 10 to the power of 1, 10 to the square, 10 cubed, etc. You get this exponential growth by just putting down more digits. In terms of learning barrier, tally mark has pretty much no learning barrier. That's all our ancestors came up with when they were still living in a cave, and pretty much everyone can understand it. Even after thousands of years, we can still understand pretty much what those people did 30,000 years ago. Roman numeral has a medium learning curve. You have to learn quite a lot of numerals to see large numbers, right? From like 0, 1 to 10 to 100, it's probably you can learn that within a week or so. But if you want to represent really large numbers, a billion or trillion, there's still Roman numerals for them, but you have to just learn them as new numerals. Positional number has a pretty low learning curve. At some point, we learn these 10 digits, 0 to 9, and then we learn that by putting them in different orders, how do we interpret the magnitude? And that's pretty much all we need to learn to understand what a number means in positional number systems. And in terms of arithmetic friendliness, tally mark is, you can barely do arithmetic. You can do addition by just copying over one number to put it next to another number, but that takes a lot of work. Subtraction is a little bit more difficult. You have to sort of like cross some of these tally marks, which is not very visually pleasing. Roman numeral, you can sort of do arithmetics, but not for some large numbers. Positional number, you can easily do addition, subtraction, multiplication, division by just lining up these numbers based on their positional weights. Right? We typically line them up based on the decimal points. And once we do that, we can just do carry propagation, borrow propagation, and then create this column method for multiplication, and eventually do really large computations even by hand. In our daily life, we deal with base 10, probably because we have 10 fingers. Transistors or computer digital systems deal with binary, and that's because they're dealing with voltages. So voltage has a low voltage, typically defined as 0, and a high voltage, typically defined as 1. So this diagram shows that we define 0 voltage to be 0, 0.35 voltage, that is my maximum, the high supply voltage, to be a logic 1. And this shows how a transistor reacts to that voltage. A transistor doesn't react linearly. At the beginning, when you change your voltage a little bit from 0, you grow it little by little, it still behaves as a 0 until you reach this cutoff point. Right? Once you go through this region, then suddenly the value will be interpreted as a 1. So the reason why this system deals with binary is because of reliability. So let's say your input voltage is 0, and you want the output to be a 1, right? 0.35 volts. And if your input voltage diverges by, let's say, 10%, 20%, 30%, for some errors, for some just fluctuations in the voltage, the output still behaves as a 0. The output doesn't change when you have 10%, 20%, even 30% deviation from your target voltage. And for that reason, it can tolerate very big errors. If you have a sequence of inverters, if they have linear reaction, then suddenly this error will propagate and they will increase. But with this kind of behavior, there's a saturation region, there's a cutoff region, then you get reliable computation with dozens of inverters back-to-back, and eventually billions of transistors back-to-back. And this class talks about digital signals. So analog signal is continuous in time and continuous in value. Digital signal does some sampling, so we only remember the value at certain time instances. And it also does some quantization by converting that continuous magnitude into a fixed bit-to-bit format. And you can sample it at every second, 10 times every second, 1,000 times every second, depending on your sampling frequency. You can store each magnitude using 1 bit, 2 bit, 10 bit, 1,000 bit, whatever number of bits you like. But that is a digital storage format where everything is stored as a series of zeros and ones. And this kind of conversion has to happen when you interact with the outside world. When you take a photo, there's some analog to digital conversion happening. When you let's say, read some data from a sensor, from a radar, there's some conversion between analog and digital signals. And if you want to see more about it, there are some EC classes that just talk about digital signal processing. The other thing we care about is the conversion between decimal and binary. When we interact with our computers, we typically type in things in decimal. Right? You have the keypad on your keyboard, 120, 129. Those are decimal numbers, and internally, all of them will be stored in binary. So this conversion has to happen at some point. So if I ask you to do this conversion, you have two choices. Number one, you just plug it into an online calculator. It does a conversion for you. Number two, you do it by hand using division and multiplication algorithm for the integer and decimal parts, respectively. So one question I ask myself is, why are we even learning about base conversion? Because in real life, you never have to do it by hand. And I think GPT provides a pretty good answer. It gives you a better understanding of number systems, how in general positional number systems work. It develops the problem-solving skills to be able to tackle problems, solve problems with the knowledge you have learned. It also, fosters a logical thinking. Working with numbers in different bases can improve our logical thinking skills, requires you to understand the rules and properties of different bases. I think those are good reasons why we're learning this. Right. So that brings us back to our learning objectives of the course. On one side, we have some concrete learning objectives, things related to digital systems, about how to deal with binary numbers, how to do Boolean algebra, how to design combinational sequential circuit, analyze them, and optimize them. On the other hand, I also outlined some of the more abstract learning objectives. Those include consider real-world problems, apply math and science, envision multiple solutions, and then analyze their trade-offs. Those objectives are very hard to concretely specify. But I think with these creative questions that go a little bit beyond the lecture, that helps you develop some of this more abstract thinking to be able to analyze a new problem and apply what you have learned in class to tackle new challenges. So here's how we do base conversion by looking at them as a bunch of positional weights. For an integer number, we have b to the 0, which is 1, and that is ignored, b to the 1, b to the 2, b to the 3. Those are the positional weights of each digit. And the magnitude of the number is just multiplying each positional weight with the corresponding numeral. In binary, every numeral can be either 0 or 1. For decimal part, we just go to a negative power. B to the negative 1, b to the negative 2, b to the negative 3. Those are fractional or decimal numbers. And to do base conversion for integer, I mean from base 10 to a target base, we divide this number by the target base. And the reason is really I want this A0 to show up in that target base. This is a visual way for us to identify one of the digits in the target base by essentially shifting that whole number to the right, dividing everything by b, so that A0 will appear as the remainder. Similarly, for the fractional part, you can again think about this conversion algorithm in terms of positional weights. All of these are decimal parts, and if you want them to show up, you probably want to bring them up into an integer. So if we multiply this whole number by the target base, the a minus 1, the first digit on the right of the decimal point, will show up as an integer. Right? It's a visual way for us to identify each digit in the target base. Right. And why can we do that? Because of positional weights. This is really something that you don't have to remember. I think I never remember this. Whenever I do this conversion, I just derive it on the fly by knowing what I'm trying to do based on this positional weight expansion. There are some special bases. Base 16, base 8, we commonly deal with these bases when interacting with computer systems, whether during programming or just getting an error screen from the normal use of operating systems. And base 16 and base 8, both of them are powers of 2. And therefore, if you want to convert between those two bases, you do not have to go through base 10. You can go through base 2 binary as the intermediate base. And all of the conversion can be done by grouping and ungrouping. The reason is really because one digit in base 16 has the same representational power as 4 bits in binary. They have the very same range, 0 to 15. Similarly, 3 bits in binary can represent numbers from 0 to 7. That is exactly one digit in base 8. Therefore, when I have these two powers, both of them are powers of the same number, a to the n, a to the m, as your basis, then you can do conversion through base a. All right, and then after that, we started talking about arithmetics, right? Before it was number representation, and now it's arithmetics. Arithmetics, there are 4 operations we care about: addition, subtraction, multiplication, division. We didn't talk much about division, so don't worry about it. We have seen many of these arithmetic in elementary school. This is an addition table. That is a multiplication table. At some point, I think we remember this in our brain. In binary, we still have these tables, but just like a 2x2 table, because your input numerals could only be 0 and 1s. So all of these operations are just a lot easier. 1 plus 1, that's the only case with a carry. 0 minus 1, 0 is smaller than 1, so you have a borrow. Multiplication works the same as decimal multiplication. All right. So one question I want you to think about is, shouldn't binary arithmetic just be easier? We already spent so many years learning decimal, and now we're spending another 2 weeks learning binary. What is the reason? Based on that table, binary is just strictly easier than decimal. Any ideas? Why did we spend like 3 lectures learning binary addition, subtraction, multiplication after we have already learned decimal so well? Yes? Negative representation, that's definitely one challenge. In decimal, the way we represent negative is just by putting down a sign. Right? Negative 7 is like negative 7, and we treat them as different entities. Right? In binary, we have to find out a better way to represent negative numbers. Therefore, we get 2's complement and 1's complement, and they have different rules. So we'll get to that in 1 second. Negative representation is definitely one concern that is unique to binary representation and binary arithmetic. Any other ideas? Yes? Cases for overflow. That's also true, right? We're dealing with a fixed number of bit widths. In decimal, when you put 2 numbers on a piece of paper, you pretty much have unlimited number of digits. In binary, we have to deal with overflow. Right? Things have to be stored in 4-bit, 8-bit, or realistically speaking, 32-bit and 64-bit format. Right? And all of the adders, all of the hardware will work within that bit width. So we have to worry about overflow. Any other ideas? Right? What makes binary arithmetic more challenging than decimal? All right. So I would like to highlight these several reasons, in addition to what we just talked about, we talked about negative representation, there's also accuracy concern. Conversion between decimal to binary doesn't work perfectly. You may run into that kind of repeating pattern. So for that reason, we do have another solution called binary codes, XS3, 8421 BCD. Those are the solutions that give you perfect accuracy. We also have to concern a lot about hardware efficiency. The way we design this adder and subtractor, we better make them reusable, with a single hardware component being able to handle both addition and subtraction, and eventually also multiplication and division. So what this tells us really, the intuition in our brain does not equate efficiency in computer systems. What we find to be intuitive algorithms may not really work in a digital system. And we're going to see that in more detail in 1 second. So again, starting with a recap of 2's complement and 1's complement. These are the 2 different ways we have seen to represent negative numbers. In terms of addition, 2's complement and unsigned, you pretty much just have to follow the bit-by-bit binary addition rule, and the result is valid. For 1's complement, when you have a final carryout, you have to bring it back, add 1 to the kind of the previous sum to get the final sum. Right? And in all systems, you have to handle overflow. In unsigned, overflow equals carryout. In 2's complement, that's when you have 2 negative numbers, but you get a 0 over here, meaning that the result is a positive number. Right? Something that is obviously wrong in terms of the sign of the inputs and outputs. That is the overflow condition for 2's complement and 1's complement. But other than that, 2's complement works just so well. You can just ignore the carry, and if there's no overflow, the remaining 4 bits will be correct. When it comes to multiplication algorithm, we are always answering 3 questions. Number 1, how to shift. Number 2, how to extend. Number 3, how to handle the positional weight at the most significant bit. In unsigned, these 3 questions are trivial. We shift by 0, we extend by 0. All of the positional weights are positive, so we just do a bunch of addition to get the multiplication result. In 2's complement, we do shift by shifting zeros. We do extension by doing sign extension. Positional weights can be viewed as a negative number at the most significant bit. So instead of the regular addition step at the end, you do a subtraction. And the reason why we care about these tasks is as follows. We need to do shift, because when we view the multiplier as a bunch of individual positional weights, some of them will have positional weight 2 to the power of k, right, a power of 2. And to calculate multiplicand times that number, you have to shift the multiplicand. Shift is a very easy operation, low complexity, and therefore that is preferred compared to doing a plain addition. We want to do extension because the result might be wider than your inputs. You have a 4-bit times 4-bit multiplication. The result could be how many bits? 8. The result could be 8. Usually 7 is enough. 8 is only for that corner case when you have the 2 most negative numbers. That's the only scenario you need 8 bits. In general, 7 bits is enough. But it's usually longer than your inputs. And therefore, when you're doing this accumulation, you want every number to fit in that wider format. So we need to do extension. And finally, we care about positional weight. Of course, that's how negative numbers are represented in 2's complement and 1's complement. By thinking about some actual luggage, some implicit luggage at the end of the number, or embedding that into the positional weight on the most significant bit to view it as a negative positional weight. So here's a summary of everything that you have to do when you do multiplication with these 3 systems. Unsigned 2's complement has a negative positional weight. 1's complement also has a negative positional weight at the MSB, but you add 1 to it. So instead of negative 16, this will become a negative 15. And you also have the corresponding shift and extension rules. But what I want to tell you is, a table of this nature could help or hurt your learning. Memorizing this table is not enough. Right? Like one way of learning is to sort of memorize the table, and then we're giving a problem, just apply the table, and then mechanically do the calculation. But what I really want you to know is why we have these rules and being able to reason about it. Right? For example, why we do sign extension and sign shift for one's complement. You probably have to put down a positive number and then try to shift it a little bit, try to extend it a little bit, and see what you need. And eventually summarize your findings into a rule. And this ability to solve problems by applying logical reasoning is what I want you to learn to get out of the class. Not by just memorizing the rule and then apply it. Because once things change a little bit, let's say I move from base 2 to base 4, all of these rules will change. And memorizing the table doesn't reflect an authentic learning. Right? But it's good, if you already know what is happening, how we derive them, it's good to have the table on the side just as a quick reference so that you can solve the problem a little bit more quickly. That's perfectly fine. All right, so coming back to this problem about negative representation. So let's say I give you this calculation, 7 plus negative 9. Of course, it's negative 2 right away. Right? But, take a pause and then think for 1 second, what is actually happening in your brain? How did you process that number to get negative 2? I'll give you 10 seconds to think about it. You may say it's just negative 2. But what is actually happening? All right, so here's what I think is happening in your brain. It happens instantly. But if you really want to break it down, you can break it down into several steps. We first observe that one of the operand is negative. So I have to probably call that function in my brain to handle negative numbers. And negative 9 is kind of hard to do with arithmetic. So you want to complement it and change the sign to a subtraction. So 7 plus negative 9 is really 7 minus 9. And 7 minus 9 is a bit easier to handle. And then you realize that the minor unit is smaller than subtrahend. So 7 is smaller than 9. So probably have to flip the operation of those two numbers. And then remember to complement the result at the end. 9 minus 7 is, of course, 2. And with the additional complement, you get negative 2. It's pretty complicated. Well, you can do that immediately. Right? Since these numbers are very small, and then you're pretty comfortable with decimal representation. But I would say, in general, if I give you like 2 larger numbers, these are the steps that you're pretty much following your brain. Like even though you may still be able to do that right away, we are internally doing a lot of processing. And these processing are just not very friendly for computer. A lot of comparison, a lot of complement, a lot of flipping, and that's a lot of operations. And if computer represents negative numbers in this sign plus magnitude format, it has to go through all of these computations, which is a lot of work. And for that reason, we have 2's complement. In 2's complement, when you see 2 numbers and you see that we're adding them, you don't have to worry about whether they are positive or negative. You just do addition. And the result, by throwing away the carryout, and if you do not have an overflow, is always correct. Right? You simply do addition without having to check the sign and the flipping the operator and any of those additional pre-processing steps. Another benefit with 2's complement arithmetic is that you can reuse the hardware. You can reuse the same 4-bit adder to also do subtraction by flipping the inputs and then add 1 to it. And this is because A minus B is no different from A plus the complement of B. And in 2's complement, we want to complement a number. You flip everything, right, by adding down these inverters in hardware, and also add 1 by adding in the carry in from that unused C0 port. So these 2 components, the adder and an adder-based subtractor, can be combined into a single 4-bit adder subtractor. This is what I showed in that demonstration on circuit verse. You have 4 adders, and then you just add in some XOR gate controlled by some operation selection signal. If the operation is 0, all of those XOR will work as a buffer. So input will just flow to the output. Nothing happened. If you set it to be a 1, all of these XOR will behave as an inverter to make it behave as a subtractor. And the operation will also become the initial carry in. So for subtraction, you have a 1 over there, all the inverted B inputs. Therefore, you get a subtractor. And there's also this overflow detection logic based on C3, C4 XOR. That's exactly the same condition of detecting negative plus negative gives you positive. or positive plus positive gives you a negative. That can be like more compactly implemented as a single XOR gate between the carry in and carry out to the most significant bit. So this discussion really gives us two good reasons to use 2's complement compared to sign plus magnitude. In 2's complement, operation is very simple. If it's addition, you just do addition. You don't have to check the sign of the inputs and outputs. It gives you great hardware reuse by being able to reuse the same circuitry for 2 different purposes. And this reconfigurability allows you to build general purpose computers more effectively. Yeah, any questions or any ideas you want to talk about? All right. In this class, we care about design, the design of circuit, the design of algorithm, analysis, how to interpret a circuit and then figure out what it does, and also optimization. So there's a bit of optimization discussion about 4-bit adder. So 4-bit adder is pretty slow in the sense that everything, the longest path in your circuit, that is called the critical path, determines the operating latency. In a full adder, the longest path will be something like going through the OP and then go through these 4 stages, right, until reaching the overflow. Or probably you start from B0, depending on which one has a longer path inside the full adder. So this could also be one of your long paths, right? And that just involves so many stages. If you have a 64-bit adder, you would run into, well, within each adder, there are 2 gates, so 128 levels. And that is just too much for realistic circuits. We talked about 2-level optimization quite a lot. In real life, circuits have somewhere between 2 and, let's say, 20 levels, maybe 2 and 15 levels. And 128 levels is just so much. You cannot tolerate that kind of latency. And therefore, people come up with some ideas to do some pre-computation by essentially get all the low-hanging fruits and do all the computation that can happen in parallel at the beginning, and then develop a large combinational circuit to do all the carry and look ahead. And what we can compute for each bit are 2 signals. Number 1 is generate. If both of your inputs going into one adder bit are 1, 1, you definitely have a carry out. You don't have to wait for the carry in. So that is a condition that directly sets the carry out to be a 1. The other condition you can pre-compute is called the propagate condition. When for each full adder, the inputs are 1, 0 or 0, 1. So you already have a magnitude of 1 waiting there. And if you have a carry in, then the magnitude becomes 2, which generates a carry out. So again, that is something that you can pre-compute. And somehow, with a smart circuit design, you can do all this carry and look ahead in a 2-level circuit. And that drastically reduces the depth of your combinational circuit. All right. So this is what we're about to see is a fun illustration of the relationship between 2's complement, 1's complement, and that original sign plus magnitude representation. It's just my take, by the way. So sign plus magnitude, you can represent number quite easily. But when it comes to arithmetic operation, you need to check for too many things. Check for the sign, flipping the operator, flipping the number, and all of these flippings. And that's just too much. Arithmetic cost is very high. And then you have these 2 newer schemes. So sign magnitude was pretty popular in the very early days of computers. I mean, 1940s, 50s, maybe even until 60s. And then 1's complement becomes quite popular from 50s to 70s to 80s until 90s. There's some calculators built in the 1990s that are still using 1's complement. And as you may know, all of the computers nowadays are built with 2's complement. And if you look at the interaction between these 2 complement systems with the original sign magnitude, conversion between sign magnitude and 1's complement is very easy, because for 1's complement, negative number involves just bit flipping. And that can be done with an O1 complexity. With 2's complement, if you want to represent a negative number, you have to flip and then add 1. And this add could propagate through all the stages. And that has an ON complexity, where n is the bit width, right? I mean the worst case. In 1's complement, 2's complement, you can both do arithmetic. 2's complement has the easiest arithmetic. 1's complement has this additional wraparound carry. And if you compare 1's complement and 2's complement, you can do conversion pretty easily by just adding 1 or subtracting 1 for that negative numbers. Positive numbers, they have the same representation. Right. So let's go back 70 years into the 1950s, and where all the computers are using sign magnitude. And let's say at that point you want to develop a new computer. Number one, we want it to be backward compatible, to be compatible with the other communications and the storage and computations in other computers. So in that situation, 1's complement may actually be preferred than 2's complement. It's easier to make this compatible with older computers using sign magnitude. Right. So the combination of sign magnitude and 1's complement really represents one equilibrium point. Within that system, communication can happen pretty easily. Computation is not too expensive. It's acceptable. But as we're having more and more computers in 1's complement, gradually the equilibrium changes. At that point, eventually 2's complement becomes more optimal. Conversion cost is not very high, and 2's complement has an obvious arithmetic benefit. And at a certain point, when most of the computers work in 2's complement, we'll just never go back. There's no reason for us to go back. They have higher arithmetic cost. I'm also incurring additional conversion costs going into other systems. So 2's complement by itself represents another equilibrium point. And this is actually the optimal landing of negative representation. But you see, the decision that people make in designing digital systems, or in deciding what kind of number representation to use, depends on the era, depends on what is the environment, what are the kind of communication protocol used by other computers. And this dynamic constantly changes. 50 years ago, 1's complement is the best. 30 years ago, 2's complement is the best. But maybe another 10, 20 years, when we have quantum computer, when we have near memory computing, all of these dynamics will change one more time. At that point, remembering how 1's complement or 2's complement works is not sufficient. You have to be adaptive. You have to know how to reason about these trade-offs and then be able to make the best decision depending on the situation, the environment, the society, the time, and all of those social factors. Some of you probably have heard about floating point numbers. So what we have seen, all of the binary numbers, even with the decimal parts, these are fixed point decimal numbers, which means you essentially set the decimal point to a particular position. You interpret everything on this side to be integer, everything on that side to be the decimal parts. You can also represent fractional and decimal numbers using floating points. Floating points is essentially a sign magnitude representation, but that's more for an arbitrary reason. The reason is the kind of creator of floating point number really likes the idea of having both positive and negative zeros, so that in some of these like high precision industrial computation, you can differentiate between like negative infinity and positive infinity. So for those very specific reasons, they picked sign magnitude, but you can perfectly design a 2's complement floating point numbers. And in floating point numbers, you have an exponent, which will be used as a power for 2. You also have a mantissa. Mantissa will be used as some numerals after the decimal points. And then this is how we represent a number. The benefit of floating point is that you can really represent very large numbers or very precise numbers within a fixed width. So let's say if you have this 32 fixed point binary number, you can represent at most, let's say if it's in 2's complement, you can represent up to 2 to the 31 minus 1 on the positive side. With floating point, you can write the exponent as, with 8-bit, you can go up to 127. And so you can represent 2 to the 127 times a number that is greater than 1, and that is greater than 2 to the 127, which is much bigger than what you can represent with a fixed point binary numbers. But the reason that we need both is because this one makes a trade-off between accuracy and precision. You can represent very large numbers that are not so precise, or very small numbers that are super precise, but you cannot represent a precise large number. Fixed point binary gives you better control over the range and precision. It is more predictable. Floating point is according to this definition, I really have no control over its dynamic range. But if you really don't want to lose anything, you want large numbers, you want full precision, binary code is what you need. You can represent every decimal digit using a binary coding, and then do arithmetic with these binary codes. And because every digit has a precise binary code definition, you can maintain the full accuracy of the representation and also of the computation. Right? Even though, as you can see, whenever you're getting something, you're losing something, you're losing a little bit on the efficiency of storage and the efficiency of operation. And these are all the binary codes that we saw in lecture. 8421, XS3, those are the two things that can be sort of used to do arithmetics because they more or less follow the positional weights. XS3 preloads every number with 3 to make the overflow detection a little bit easier. 8421 follows the regular binary sequence. 2 out of 5, that is a code that you can use it to represent number. Arithmetic is probably not so friendly, but you do have an error detection property with that code. All of the binary numbers have 2 ones out of the 5 bits. So whenever if me as a receiver receive the message with 3 ones, I know something has gone wrong. So by using some extra bits and embedding some redundancy, you can do error detection. A Greek code follows this sequence of bit flips that every adjacent number only differs by 1 bit. So 1 bit flip, 1 bit flip, 1 bit flip, 1 bit flip. All of them have a 1 bit flip. And that one doesn't have much use in communication or computation. But this idea of adjacency is coming up a lot when we deal with Boolean minimization. We think about Carnot map. They follow that kind of order for 2 bits. 0001, 1110 is a 2-bit Greek code. And we're going to see that just a lot more in the coming days and coming weeks. Right. So XS3 is this very cute idea, where to do addition, you preload every number by 3 so that when your magnitude reaches 10, the 4-bit binary representation reaches 16 to produce a binary carryout. At that point, binary carryout equals the decimal carryout. All right, and carry is usually the longest path in your circuit. And by being able to optimize the latency of the carry chain, you can accelerate your overall multi-digit computation, like multi-digit addition or subtraction. This is actually one of those things that appear in every textbook. Every digital design class talks about it. But I think it never gets used. And I really don't know why. Right? There's some things with good mathematical properties that lost all the tractions in real life. Probably because it's a little bit too redundant. You have to really preload 3 to each number, do this pre-processing and post-processing. After addition, subtraction, do a correction step. And probably for those reasons, this one never gained much interest in real life. All right, so that's pretty much everything about binary numbers, representing numbers, arithmetic with numbers, or even with binary codes. And the next thing that we talked about is error detection and correction. You send me a message for all kinds of reasons, noises, faults, losses, attacks, errors. The message might be corrupted on the receiving end. And it would be ideal if I can either identify that error has happened or be able to correct the message, depending on the application scenario. Let's say for credit card, remember that example. For credit card, I only want detection but not correction for safety reason. For communication, it could be either detection or correction, depending on the kind of security or sensitivity level of that communication protocol. 2 out of 5 code has the error detection capability. Correct codes have 2 ones. Incorrect codes would have a single 1, 3 ones, 4 ones, 5 ones. But whenever I see anything but 2 ones in my 5-bit message, I know that it is not correct. And this idea can be generalized into parity codes, which takes the original message, any number of bits, and we can add in 1 additional parity bit to monitor whether I have an odd or even number of ones in my original message. If that number is, if I have an odd number of ones, I'm going to put down a parity bit of 1 to make the total number of ones an even number. If I already have an even number, the XOR function will produce a 0. Again, my 5-bit message has an even number of ones. And with that, the receiver just have to confirm whether there is an even or odd number of ones. If it's even, it's correct. If it's odd, it's incorrect. Hamming code is just a way to put down 3 parity bits at those particular positions. The idea is very same as a 1-bit parity, but now we're using different parity bits to monitor different positions so that each position affects different parity bits. And then by checking the correctness of all the parity bits, you can actually locate where the error happens. And again, keep in mind that when we talk about this error correction, there's a receiver, there's a sender. So the sender first computes the parity, send this expanded message to the receiver. The receiver checks the correctness of the parity bits by maybe looking at that table or checking this equation to compute the correction code word. And at that point, he'll make the correction and then extract the original 4-bit message from the 7-bit message. So correction calculation and parity calculation happen at 2 different parties. All right. I hope you still remember why Hamming code is ordered like that, right? How do we derive that kind of correction equation? And that is really because we represent each position as a binary number, and we want this correction code word, C2, C0, C1, C2, to be used as a binary number to index into one of the positions. So if I have an error at position 7, so I'm 0, I want all of my correction equations to change so that I have a 111 reading. And for that reason, M0 is included in all of the 3 correction equations. Similarly, M2, that is position 5, represented as 101 in binary. So I want my C0 and C2 to be impacted by an error at M2, and therefore M2 appears in both the top and bottom equations. And you remember in the workbook, you tried to build an XS3 correction code where you just essentially put down the XS3 representation for each position and then develop the correction equations accordingly. And parity equation is nothing more than the correction equation minus the parity bits. Come back here. Parity equation is essentially the correction equation by getting rid of the corresponding parity bits. Getting rid of P0 in the C0 equation, P1 in the C1 equation, P2 in the C2 equation, you get 3 parity equations. All right. And Hamming code allows us to do 1-bit correction, 2-bit detection. That's because it has a minimal Hamming distance of 3. In general, you can reason about the error correction detection property by only looking at the minimal Hamming distance. If the minimal Hamming distance is n, you can do any error detection for up to n-1 bit, because you really need at least n bit flips to go from one valid number to another valid number. n-1 bit is just not enough. So n-1 bit will land you into an incorrect number or incorrect code, and therefore you can detect it. To make error correction, the idea is to bring back every code word or erroneous code word into its nearest neighbor. So you cannot go more than halfway between 2 valid numbers. So if they differ by Hamming distance of 3, as illustrated in that example, and you have 1-bit flip, then you can bring back to the original number, the original code word as the nearest number, the nearest neighbor. But if you have 2-bit flips, the nearest neighbor changes to another valid code word, which is not the original. So you can no longer make error correction. Right? So this formula is really saying it's smaller than n divided by 2. All right. So that's about error correction. So we talked about binary stuff, representation, arithmetic, and then error correction. And now we are moving on to Boolean algebra, which is a gateway towards designing combinatorial circuits to eventually support all of those binary manipulations that we played with earlier. And Boolean algebra was developed by George Boole, which is motivated by work of De Morgan, De Morgan's formal syllogism. And I only recently realized that De Morgan has a lot more contribution than Boolean algebra. He's a mathematician, and he has also studied the kind of 4-color theorem, where you can color a map with 4 colors while making sure that all the adjacent regions do not have the same color. So he was an advocate for that problem at the beginning, and that turns out to be, eventually, after another 100 years, to be the first theorem proven by a computer. At that point, computer-based proof was not widely accepted, so that raises quite quite a bit of debate in the mathematical community, but all of that comes from De Morgan. So Boolean algebra has application in designing logic and hardware. When you do programming, you have these operations and or XOR. Essentially, you're dealing with Boolean algebra. In hardware design, all of the gates operate according to Boolean algebra. And just in general, learning Boolean algebra also helps you to become a better programmer. You can optimize your code, the if conditions a lot better by being able to optimize it. Instead of writing it as a case of 16 different scenarios, you can probably do some optimization to write it as only like 2-3 cases. And Boolean algebra eventually evolved into abstract algebra. When people deal with lattices, where you have 2-dimensional kind of points in a space, rings, fields, modulus, when you study things like cryptography, you're going to see a lot of those. So CSE 107 or Math 100. And also quantum computing, privacy-preserving computing. Many of them are built based on abstract algebra. And many of the principles, the theorems and axioms in abstract algebra follow the same as Boolean algebra. So this is a formal definition of a 2-valued Boolean algebra. We're defining 2 elements, 2 operations, and each operation has an identity element. Identity element allows you to satisfy the identity axioms. And commutativity, you can flip the input order. Distributivity, you can apply distribute addition over multiplication and also multiplication over addition. Right? In both ways, that's a unique feature of Boolean algebra that does not remain valid in the ordinary algebra. Identity is by definition. Complement is saying that 2 elements will give you the identity element of the other operation. That's the interaction between these 2 operators. Right? They interact through the complement axioms. One could be, one is a 1 over here, but it's really the identity element of the other operator. When you have a more general 4-valued Boolean algebra, for example, you may not have a 1. You just have to replace it with the identity element from the other operator. And formally speaking, there's also closure and cardinality. Closure is just saying that the output should be one of your input symbols. You cannot have 0 plus 1 equals 2. All of the outputs have to be 0 and 1, same as your input space. And cardinality is saying that you have to have at least 2 elements in Boolean algebra. Right? So those are like trivial truths pretty much. You don't have to worry about them. All right. So Boolean algebra can be used to manipulate Boolean expressions. By manipulating, I mean simplify it, proving equality, or just in general do transformation between 2 expressions. This is an POS, a product of sums, which, when translated into a circuit, has an AND gate at the end and a number of OR gates at the front. If you want to convert this into an SOP, to an SOP, you can always apply distributivity. It always allows you to go from any place to sum of products. But the thing with Boolean algebra is that you can go through that route, but it's a lot of work, right? A lot of variables, and then if you want to multiply all of them out, you would have 3 times 3 times 2, which is 18 different clauses, right? Different product terms. And you have to do some additional simplification over there, which is a lot of work. Alternatively, you can probably spend a bit more time observing the equation to see what are something that can be factored out, that can be simplified at the beginning to eventually eliminate the number of distributivity I need to apply. And based on that expression, what I observe is that the first 2 terms share A prime plus C prime. That is a common subexpression between the first 2 terms. And in general, by taking advantage of this observation, things that are common between 2 terms, things that are complement between the 2 terms, you can apply distributivity in a different way, or you can apply elimination, you can apply consensus to simplify the procedure, the steps of your Boolean algebraic proof. And in this case, once I apply distributivity on A prime, I miss a prime over here, A prime C prime, then BD can be seen as a complement of B prime plus D prime by De Morgan's theorem. And therefore, this can be eliminated by the elimination theorem. And then you have to apply still distributivity, but for a much smaller expression. So this example shows you that when you do Boolean algebraic proof, you can go through multiple sequence of axioms and theorems. And finding the best is usually not easy. But there's something that you can take advantage of, the observation that these terms, A prime, C prime, are common. So taking advantage of those observations as much as possible before you apply a brute force method. All right. Yeah. Any questions so far? All right. So I want to tell you a little bit about the distinction between workbook and exam. So in the workbook, we have all kinds of questions, going from some very busy work, let's say applying Boolean algebra, like finding the minimum expression from a large function. And I think those are, I'm afraid that those are necessary when it's the first time that you're learning a topic, and I want to give you a bit of practice. But in the exam, there's minimal busy work. The workload is very minimum. If you ever see something like more than arithmetically more than what you can compute with 2 hands, or algebraically more than 10, 12 literals, you probably have to take a pause and then reconsider your strategy and find a better way to solve the problem using a non-brute force method. Right. So if you ever run into any of these, right, things that are super complex, super puzzling, try to apply some logical deduction to connect them to what you have learned to simplify the problem. So again, these are the learning objectives of this course: design, analyze, and optimize combinational and later sequential circuit. But for now, we're dealing with combinational circuit. So design optimize represents the flow where you go from some specification. So let's say I'm trying to create a 1-1-0 comparator. I'm trying to create a 4-bit adder. That kind of behavior description into a Boolean circuit, a circuit with gates. Gates and inputs and outputs, those together defines the combinational behavior. On the other side, analysis is a way to go from a circuit back into the specification, to essentially plug in some values into the circuit to see how it reacts, or to derive the expression based on a circuit. We've seen that for a adder. This is a 1-bit half adder, an adder without the carry import. Following the basic binary arithmetic rule, you can draw the truth table, convert that into an expression, and then finally draw the circuit diagram. You can also go it the other way around. From there, derive the very same expression that corresponds exactly to that circuitry, and then put down the truth table, figure out that we're doing an addition over here. That is about completely specified function. When all of the input patterns are specified and could occur, we also have incompletely specified function, where certain input combinations, like one over here, are known to never appear. And therefore, you can make use of it to optimize your circuit even further. You can try to assign this to be a 0 and see what you get as the implementation, assign a 1, see what you get, and compare the two to figure out the better implementation. Better, it could mean fewer transistors, fewer gates, fewer gate inputs, lower latency, lower power, et cetera, right, depending on your optimization objective. So don't care gives you a choice. You may have to navigate in this space of choices to find out the best. Right. And once you put down a choice over here, so let's say I assume this to be a 1 so that I have an OR gate implementation, and then I do the implementation, it's no longer possible for me to go back. All the don't care information gets lost in the implementation process. From the implementation, the only thing I know is that 1, 1 produces a 1. And in fact, all the Boolean circuits and Boolean expression are fully specified, because you can just plug in any value into the circuit, and it will give you a result. There's no such a thing as don't care in the implementation. Right. So therefore, for a fully specified function, you can go both ways, specification to implementation, and then back to specification. For incompletely specified function, you can implement it by assigning certain values to the don't cares. But once you assign that value, you cannot reverse the process unless you get more information. Right? Like in these workbook questions, we give you a little bit more intelligence about an SOP and the POS. So with multiple pieces of information, you can do a complete reverse engineering and then reconstruct the original truth table with don't care conditions. Right? This simply shows that engineering, it's not easy. Right? Finding the best implementation is not easy. Reverse engineering is even more difficult. But you do need both skills because reverse engineering essential part is not just for malicious purpose. Reverse engineering is also used for things like debugging, diagnosis, improving your design. It happens all the time for just the designer. As a designer, you need to do reverse engineering. Similarly, as a programmer, sometimes you also have to reverse engineer the codes written by other people, and that is also a reverse engineering. So when dealing with both software and hardware problems, engineering, which is implementation, and reverse engineering, which is analysis, are equally important. All right. Algebraic proof is difficult. Therefore, people come up with a better tool, the Carnot map, which gives you a much better visualization about adjacency relationship to allow you to more easily group together zeros and ones to create implicates and implicants, and eventually create a minimal expression. And Carnot map is derived from the width chart by flipping the column order to increase adjacency. But also you have to assume this end-around adjacency on the side. And if it's a 4x4 K-map, the top and bottom adjacency and the corner-to-corner adjacency. To find a minimal expression from K-map, we need to group together zeros and ones. Well, if it's a sum of products, we care about ones. We're trying to find product terms, which translates into a block of ones in the K-map. And once we found some blocks of ones, we need to figure out which of them are essential. The essential implicants are essential by definition, which means they must be included in the expression to be able to cover all the ones with prime implicants. So in this example, we have two essential prime implicants, and both of them must be included in my final SOP expression. And this gives us a nice algorithm to approach the logic minimization problem. Again, with Boolean algebra, you can do minimization, but it's difficult. You just cannot easily eyeball the optimization sequence. With K-map, you have an algorithm. The algorithm is to first identify all the essential prime implicants, include them in the expression, and see which are the remaining midterms that have not been covered. And I'll just have to search for a way to best cover them. In this case, they can be covered by a single implicant. Essential prime implicant represents a classical technique to write algorithm, which is pruning. Instead of tackling a problem altogether and then give yourself a very large search space, you can do some pruning by identifying information that is necessarily needed using a greedy algorithm, and subsequently maybe apply a brute force method to only the remaining smaller problem. And questions? All right. Yeah. Any questions? All right. So that's pretty much everything that we have seen so far. Binary numbers, arithmetic, binary codes, error correction, Boolean algebra, and later logic minimization using Boolean algebra and Carnot maps. All right. So I would like to remind you what I outlined on Monday of week 1 about the coverage of CSE 140. So we're operating in the context of digital design. All of these things that we talked about are either binary or Boolean, which are strongly circuit related. But I think the course is also about algorithm, right? Different logic minimization algorithm, applications, analysis, and theory about numbers. Here are these different aspects that you have seen in this class. In terms of algorithm, we have developed algorithms for base conversion, addition, multiplication, grouping, ungrouping, for binary number and code arithmetics, how to detect overflow, how to propagate the carry, and how to make corrections. Error correction, right? It's a way to ensure the reliability of communication between the sender and receiver, and logic simplification. There's an algorithm with Boolean algebra and an algorithm with K-map, but the K-map algorithms are not better. In terms of theory, we talked about number theory. For example, when we talk about Hamming code, we added 3 additional bits to just give us enough power to differentiate 8 different scenarios. That's a number theory. We talk about Boolean algebra. This is a new algebraic system. We talk about information theory, about error correction detection, and different abstraction levels. We'll go from specification to implementation. They essentially you want them to describe the very same thing, but they happen at different abstraction level. There's a very high level, a more intuitive representation, and a very low level, which is not so intuitive but friendly to implementation. All right. We have seen many tools that can help us to simplify our job. Truth table is a way to represent Boolean functions. Circuit diagram is a way to visually see the implementation without having to deal with transistors and metals and all things of that sort. Right? We have seen expansions, midterm maximum expansions, sum of products, product of sum. These are like common representation tools. And finally, we have seen K-map, which can be used to both represent functions with or without don't cares, and also perform logical minimization, and also visualize, plotting different expressions in that more adjacency-friendly format. And finally, we have been doing our analysis and discussion in different applications. We talk about the vehicles. We talk about how to map a realistic behavior description into a pretty detailed and concrete specification in the form of a truth table, and eventually get into an implementation. We talked about some of the concerns in the communication protocol, which are error correction and detection. And those are important for also security and privacy and reliability purposes. And finally, things like universal gate can be used to apply the capability of new technologies to be able to implement any computation by only needing to verify that they can implement AND and OR and inverter and XOR and OR, a set of universal gates. All right, so this is what I have talked about before. So here's where we are in this course. We have covered nearly half of the class. We're at the middle of the term, so that's what you should expect. We are halfway in this combinational design and optimization problem. We have seen design optimization using Boolean algebra and K-map. And after the midterm, for the rest of week 3, we're going to see some additional combinational minimization algorithms, a way to handle more than 4 variables. Essentially a computer algorithm format. And after that, when we move on to week 4 and week 5, we're going to talk about sequential elements and sequential design and minimization. Right. So that's for the rest of the quarter. And here are some reminders for you. The exam is tomorrow, of course. I hope you all know that already. Workbook today, there's a workbook today, but there's no question. Essentially, you just have to tick a box to indicate that you have done an online survey after the exam. So please do it after the exam, because there are some questions related to the exam. And be sure to get things back on track right after the midterm. So on Wednesday, we're going to immediately continue our conversation with logical minimization. So there's really no time to take a break in the summer session, I'm afraid. So that's everything I have for today. And I'm happy to take any further questions that you have maybe related to anything, lectures, workbook, the upcoming exam. Any questions? Yes?
What's the best energy drink to study?
24-hour energy.
Can you explain the Hamming distance again? Like Hamming distance, and like all that?
Yes, yes. So minimum Hamming distance examines all the valid code words that you defined. So let's say 2 out of 5, you're defining those words with 2 ones to be valid. Then measuring within any pair of elements within that valid set, what is the minimum Hamming distance? And Hamming distance is the number of bit differences between 2 numbers. So if you look at 2 out of 5, for example, right, take any 2 numbers. What is the minimum Hamming distance? OK, so I'm saying, I need to check every pair to see how many bits they differ at least. So let's say these 2 differ by 2 bits. Right? These 2 differ by 2 bits. These 2 by 2 bits. And maybe this one and the top one, they differ by 4 bits. Top and bottom differ by 4 bits.
Wait, how do you know the difference between each bit?
Oh, so I'm comparing 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. I'm comparing them bit by bit. The first bit is 0 there, 1 here, so they differ. Second bit, 0 and 1, they differ. Third bit, 0 and 0, same. 1, 0 differ, 1, 0 differ. They differ on 4 bits. Right, 4-bit positions out of the 5 positions. And therefore, if you look at all the codes, at least 2 numbers differ by 2 bits. You cannot find 2 neighbors. I'm just checking all the combinations, assuming that I already examined all the 90 different combinations. Right? All of them differ by at least 2 bits. All right? And with that, let's say if you send me a message from one of those numbers, and there's only a 1-bit error, the error cannot bring your code from one valid code to another valid code, because two valid codes differ by 2 bits. And 1-bit error is not capable enough to confuse me. So 1-bit error will bring you into this invalid region, a code that is not valid. And therefore, I can tell that an error has happened.
Can you give two like example like on the whiteboard? I guess.
Oh, okay.
Yeah.
So if you send me 0, 0, 0, 1, 1. Right. So this one has an even number of 1, has essentially 2 out of 5. Right. And if there's a 1-bit error, how many 1s do you have in the code? By 1-bit error, I mean one of the bits gets flipped. So if the flip happens at one of these 3 bits, you would have 3 1s. Right? If the bit flip happens at one of these 2 bits, you would have a single 1. So after a 1-bit error, you would have 1 or 3 1s out of 5. And because I know that I should expect a 2 out of 5 code from our communication protocol, single 1s, 3 1s, those are invalid codes. So I know that something has gone wrong during the communication. Does it make sense?
Yeah.
Right. And then the minimum Hamming distance is a way to measure in general how many bits of errors are needed to confuse me, so that these errors will mask out with each other to appear as another valid code word. So in this case, if you have a 2-bit error, if there's a 2-bit error between our communication, right, you might get, let's say, 00110. Okay, you send me this. There's a 2-bit error. I receive this. There's no way for me to tell whether this is your original message or a message after 2-bit errors. This could be your original message because it's a valid 2 out of 5 message. This could be this message after a 2-bit error. I just have no way to tell. Because 2 valid codes only differ by 2 bits, and if there's a 2-bit error, it's perfectly capable of bringing one valid code to another valid code. At that point, I'm no longer able to tell whether it is truly valid or it comes out of a 2-bit error from another valid code.
So how do you, if you were on the test, I think like one of the test on an arrow bits and parity bits, how would you, based on those information?
Yeah, that's actually a different question. That's a question about information theory. Like, having 3 parity bits allows you to differentiate 8 different scenarios to cover 4 message bit, 3 parity bit, and one case for the no error situation.
Yeah, like how would you do that?
For that, let's say if I have a 25-bit message, right, I want to add a few parity bits to it, right, to be able to essentially describe a 1-bit error at any of these positions, plus an additional case of having no error.
Wait, sorry, can you use like a more
Okay.
like color marker?
Sure.
Because like how many parity bits do you need to add to a 3-bit message? Or like the question is.
Okay. So you're asking a specific question. So could you tell me the question again?
Wait, actually, let's do this question. Bit orders reversed. For example, 11000011 is a symmetric code. How many bits of parity?
You're asking. Are you asking one question, or is it that 3?
Question 5 on the practice midterm.
And by the way, I have to remind you that this is not a practice midterm. But I see what you're saying. Yeah. Yeah. How many parity bits do you need to add to a 3-bit message to correct 2-bit errors? We have a formula that tells you, let's say you have M message bit, and let's say P parity bits. And if you want to make 1-bit error correction, here's what you need to satisfy. You need to make sure that 2 to the p is greater than or equal to m plus p plus 1. This is for 1-bit error correction. Because with 1-bit error correction, you want these additional parity bits to be able to describe several scenarios. Message at one of the message bit, error at one of the message bits, error at one of the parity bits. And you have to reserve one representation to show the no error case. So this has to be true. With the regular Hamming code, we have 2 to the 3 greater than or equal to 4 plus 3 plus 1, which is an optimal construction. Right? They are equal. So you have enough information. And if you embed these parity bits properly, you just have enough information to differentiate 8 different scenarios. And we reserve 4 of them to describe a message error, 3 of them to describe a parity error, and 1 of them to describe the no error situation. All right, so let's say in that question, how many parity bits do you need to add to a 3-bit message to correct a 2-bit error? We're talking about 2-bit error correction. I would say 2 to the 3, so 2 to the p. These are, again, the number of scenarios that you can describe. Has to be greater than all the possibilities of 2-bit errors. What do I mean by 2-bit error? I mean 2 of the bits get flipped. And that would be something that m plus p choose 2. These are all the scenarios I need to describe. That's fine. That's the reason why it's not an exam question. No, you didn't learn this. Oh, you learned this formula. You learned this formula, but not this. Right. Like I wouldn't call this an unreasonable extension, but the exam questions are not as creative as this one. You get the point? All right. And let's say 2-bit error, you still have to reserve that, one scenario for the no error communication. And sometimes when we talk about 2-bit error correction, it also includes 1-bit error. It's saying really up to 2 bits. Right? 2-bit error typically means up to 2 bits, unless we tell you exactly 2 bits. So you have to again include m and p. Again, like these are all the 1-bit error. These are all the 2-bit error. This is the 0-bit error, kind of no error case. You need to have enough expressive power to represent these scenarios, these many scenarios. Okay, yeah, question 5. Yeah, this is a lot more reasonable question. Similar to what you were asking earlier, the minimum Hamming distance. Right? So let's say we define a new invariant. So 2 out of 5 is an invariant. It's a property that all the valid codes need to satisfy. Symmetric is also an invariant. It's a property that all the valid codes need to satisfy. So let's say 0, 0, 0. How many bits? 8 bits. 0, 0, 0, 1, 1, 0, 0, 0. This is a symmetric code. And the nearest neighbor to this would be something like you change 1 bit on the left, which will cause another bit flip on the right. And they differ by a Hamming distance of 2. And because of the symmetric property, you cannot construct 2 valid codes that differ by only 1 bit. If they differ by 1 bit on the left, they'll also differ by 1 bit on the right because it's symmetric. So 2 valid numbers differ by at least 2 bits. So their minimum Hamming distance is 2, which allows you to do 1-bit error detection and 0-bit error correction. Okay, so I'm trying to find a pair of codes with the minimum Hamming distance. And that number is 2. Because let's say if I think of this as a symmetric code, if the left side differ by 1 bit, the right side will also differ by 1 bit. So they differ by at least 2 bits. Right? The same is the same. If they differ by 1 bit, they differ by at least 2 bits. So for any pair of codes satisfying this property, they will differ by at least 2 bits. It could be 2, it could be 4, it could be 6, it could even be 8 bits, but it's more than 2. Yes. No, we assume the error only happens on one of the bits. So it only flip one side, right? To cause it to essentially be non-symmetric. And that's also the reason why we can do 1-bit error detection. Right? But you can also reason about it in terms of minimum Hamming distance. You need at least 2-bit flips to go from one valid code to another valid code. The answer is you can do 1-bit error detection. Because minimum Hamming distance is 2, that allows you to do 1-bit detection and 0-bit correction. You can now do correction. Yes. Yes. Hamming distance, yes. The minimum number of positions where these two numbers, the minimum, anyone has a good description of, yeah, Judy? The minimum, yeah.
Wait, how do you know, like, if
No, that would be too much work, isn't it? Right? But if I could describe this kind of property, you can reason about minimum Hamming distance by reasoning about its symmetric property rather than enumerating all the codes. And that would be a reasonable question. Like I wouldn't just randomly throw at you like 10 different binary numbers and expect you to find out the minimum Hamming distance, because that does require a lot of pairwise comparison. But if there's a certain pattern or a certain invariant property, right, you can more easily reason about Hamming distance, minimum Hamming distance.
Can I ask another question? Just right now, like the broadcast you're recording, just gonna.
Sure.
Wait, can you explain why do we add the 1 at the end?
One's complement addition.
Yeah, why do we add a 1 like or 0 or whatever?
Okay.
Like why we do what we do, like.
Yes. So think about them as unsigned y. The y question is very hard to answer, but think about this as all of them as unsigned numbers. So this is unsigned 7. This is unsigned -4 plus 15, which is 11. This is 11, right? 7 plus 11.
You know this, like for the exam, but not for whatever.
You need to know this.
For the exam.
Well, I can't answer you like for the specific question, but this is definitely one thing covered.
Oh yeah. Okay.
Yeah. So 7. The reasoning of the why. You not necessary. Not be. You don't have to be able to explain it, but you sort of have to understand why. But like I wouldn't ask you like a strict question like tell me why you do and run carry. But I expect you to be able to explain to yourself why that is the case so that you can essentially apply the very same analysis to similar problems. All right. So 7, this is 11 unsigned, which is -4 plus 15. Here, you have a carryout. In terms of unsigned, that's 16. And then let's say we throw it away. Right? We're throwing it away, sort of. So we're throwing away 16 out of the unsigned magnitude. But what you really need to throw away is only 15. The actual luggage of this negative number is only -15. So you want to throw away 15 to get a positive number, but you have thrown away 16 by ignoring the end around carry. So you need to add 1 back. So you need to throw away negative 15. You have thrown away 16, so you need to add 1 back. 15 is the definition of 1's complement. This negative number carries actual luggage of negative 2 to the n minus 1 minus plus 1. 15 is by definition. So negative number carries this luggage, negative 2 to the n minus 1 plus 1. So negative 2 to the 4 plus 1. 4 is the bit width. Sorry, it's without the minus 1, without embedding. So this is negative 15. I think of this the extra luggage carried by a negative 1's complement number. That's how we reinterpret this binary string into a negative number. We cannot just read out the regular positive positional weights. We have to assume that there's some negativity that it inherently carries. Yeah, let me first take the question from Melissa. Yeah, it's kind of similar. You can always reason about them in terms of the actual luggage or the excess. Right? This one just has a different kind of excess, like on the negative side. But yeah, you sort of like this one has been preloaded with 15. And then in terms of unsigned, you are throwing away 16. And this one has only been preloaded with 15. And when you come to a positive result, you have to throw away 15. But by ignoring this, you have thrown away 16. So you have thrown away that 1 too much, so you have to add 1 back. Like this, being able to explain why things work the way they do is more like an implicit understanding. You don't have to be able to articulate it, but you have to know why. Yes, Judy. Yes, assume it's a 4-bit number. Yeah. Yes. Yeah, I only move it when I have the actual carryout. But this movement doesn't really mean anything. This is only like an easy way to remember it. But really, it is you are throwing away and then you're adding 1 back as a compensation. But visually, you can think of it as carry being added back. And it only happens when you have a carry.
How you get 15 or 16? Do you just remember? Or?
You could. I'll show you 3 ways. Number 1 is to remember this negative 15, negative 16. Number 2 is remember that for 1's complement, you do complement by flipping out the bits. So a negative number and a positive number. So let's say 0, 0, 1, 1, 1, 1, 0, 0. These are like 3 and negative 3, respectively. And they add up to 1, 1, 1, 1. This is an alternative definition of 1's complement. Like somehow negative number and positive numbers relate by 15 in unsigned. And for 2's complement, 0, 0, 1, 1 is positive 3. Negative 3 would be 1, 1, 0, 1 in 2's complement. And they add up to 1, 0, 0, 0, 0, right? 2 to the n. That's a different definition of 2's complement. The relationship between these positive number and negative numbers are according to 16 and 15, respectively. And if you go, the other direction, it would be a negative number carries a negative 15 luggage. All right, or you can just think about these 2 examples and then figure out the luggage by yourself. 1, 1, 0, 1, that's a complement of positive 3, so this is negative 3 in 1's complement. And if you look this as an unsigned number, that is 12. Negative 3 and 12 differ by 15. So there are many ways you can get to this number.